Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to be finishing up our conversation on phase transitions by looking at kind of a nuanced topic of how we can classify our phase transitions using a technique called the Ehrenfest classification system. So far we've talked about several key properties of systems. So we talked about how chemical potentials can change for both pure substances and for phase transitions. And then we use that to try and look at how physical properties change along our various phase boundaries. And then we've also looked at how these physical properties change for a pure species. So we can kind of go ahead and compare these changes in physical properties for pure species and phase boundaries to try and categorize phase transitions based on how these properties differ. And specifically, we're going to look at how they change with temperature as I go past the phase boundary. So these systems are this classification of properties is known as the Ehrenfest classification system. And it's a good review of how we look at these various temperature-based changes. So it's worth noting that all phase changes tend to involve a continuous change of chemical potential with temperature. So as I increase the temperature, the chemical potential will change continuously. There will be no abrupt shifts or jumps. However, when we are looking at volumes, enthalpy, entropy, and heat capacity, in most of our classic phase transitions, these will have spontaneous changes. And so they're said to be discontinuous. And these type of more typical phase transitions are known as first order transition. So think about last time when we were building up our phase boundary definitions, we talked about a lot how we have a change in molar volume. Because a lot of times as I go, say, from a liquid to a gas, I'll have a spontaneous jump in my volume, and I'll have a discrete change in molar volume that will very much uh, describe how this phase transition goes. However, we have a continuous change as I'm heating up my solid liquid and I'm heating up my gas. So we have a continuous change, then a discrete jump, and then a continuous change. We also have a very similar thing with enthalpy, because remember, as we have a phase transition, we have an enthalpy of transition. Means I have a discrete jump. This value is very rarely zero. So it means I pop up from, say, my enthalpy for the liquid, and then suddenly when I go to the gas, I have a very different enthalpy. And it's worth noting, this is often how we actually determine where the transition temperature is I add heat, I have a nice continuous change with temperature, and then the temperature stops changing while I undergo a phase transition. And this can be a very good way of both figuring out my enthalpy of transition, but also of a good way of determining that melting point or boiling point. Now, chemical potentials, I said these are continuous, but note that there is an inflection point here. So while the value of chemical potential is continuous, the first derivative is not. We have a change with the chemical potential and then another discrete change, which makes sense because my entropy is discontinuous and the chemical potential changes with temperature as a function of entropy. And again, just if I have a discontinuous enthalpy, I should also have a discontinuous entropy. Because remember, at equilibrium, these two are going to be related. Now, the heat capacity gets a little interesting. So typically, I have a lower heat capacity for my higher temperature substance. So I have a lower heat capacity for a liquid than a solid and a gas than a liquid. But because I have to put in a lot of energy to make that temperature change around the phase transition point, usually we have technically have a very large jump in the heat capacity at that point. We just tend not to treat it as a heat capacity, instead call it the enthalpy of transition. And this is the behavior we expect for most of the phase transitions we've talked about before, or these first order phase transitions. So almost all the time when I go from a solid to a liquid, or a liquid to a gas, or solid to a gas, I'm going to have a first order phase transition. However, there's some substances that manage to have what are called a second order phase transition. In this case, we have a continuous change with molar volume, enthalpy, and entropy. And because the entropy is continuous, I also have a continuous first derivative in my chemical potential, but I do have a change in the second derivative. And the reason why I'm going to have, but notice the heat capacity will still be discontinuous because of that change in enthalpy. Now, what is actually going to be involved in one of these cases? Well, the real hint here is going to be on what happens with the volume and the enthalpy. In this case, what happens is that I'm changing the temperature. The volume for both of my phases are going to be the same at this point, but how the volume changes is going to differ. Now, what this often means is that a second order Ehrenfest transition is often going to be a solid-solid transition, so they both have the same density at a given temperature. But what happens is that suddenly I rearrange that crystal, or the crystal starts growing in a new way. And there's some sort of easy overlap in between those two systems, so they can change the phases. But because they have a different crystal structure, that means they're going to respond to temperature and pressure very differently, which is the reason why I have a continuous volume, but a different derivative for volume, enthalpy, and entropy, as well as a different way they'll take up different amounts of heat to change from there on forth because they're expanding differently. Now, these are kind of hard to imagine, but there is a very classic example of a second order Ehrenfest transition, and it's something called tin past. So tin actually has two different major crystal structures. So the most stable version of tin that we often think about is something called beta tin. And you can kind of see this kind of fun octahedral lattice here on the right. And this is the crystal structure of beta tin. And when you think about tin, you're often thinking about beta tin. It's relatively ductile, it conducts electricity, it's nice and kind of silvery. Alpha tin, however, is a tetrahedral lattice. And because of this, it doesn't share electrons so well and is a lot more rigid. So it tends to be larger, it tends to be more brittle, and it tends to not conduct electricity. Interestingly enough, they have a second order Ehrenfest transition. So at about a temperature of about 13 degrees Celsius or about 55 degrees Fahrenheit, they will have the same molar volume and you can go from one to another. However, because of kinetic reasons, usually the transition doesn't happen at these conditions. Instead, what we find is that this alpha tin is going to be more stable at low temperatures and beta at high. So if you drop the temperature below about negative 30 degrees Celsius, but it'll start to happen significantly below zero, especially below 0 Fahrenheit, about negative 20 Celsius, you can start to convert this beta tin into alpha tin. And this is called tin past because now your nice, beautiful, shiny metal starts falling apart and expanding and become very brittle. And all we had was a change in crystal structure. And the most iconic example of this is there's a classic story that in 1812, when Napoleon was invading Russia, they started off in the summer and everyone was fine. When they had to retreat and marching back from Moscow, the temps started to drop below negative 30 Celsius. And this caused all of the buttons on their coats, which were made out of nice shiny tin, to undergo tin pest. And their buttons started falling off, which made it much harder for them to stay warm in that cold, chilly winter. So again, this is also one of the reasons why tin has to be used very selectively under temperature conditions, lest it succumb to tin pest. So next time, we're going to go ahead and start in on chapter 5, as we're going to move from simple phase transitions to starting to examine mixtures. Until then, take care.